Good afternoon. Thank you for joining us today for this webinar, our mini-STEMposium to support teachers in the field. This is the 6th of 18 webinars we are hosting. This session has 202 people attending. My name is Ken Heydrich, and I am the National STEM Manager for Accelerate Learning. I'll be your host today for an incredible afternoon of learning. I've been in K-16 education for over 30 years. Connecting with educators in the field, like today, is the best part of my day. Thank you for being here. We have lined up some exceptional talent from around the country for these mini-STEMposiums. This week, we offered 6 sessions during the afternoon. We will also host 6 sessions in June 16 through 18, and 6 sessions during July 14 through 16. The link to the schedule is found in the chat window. Some of our national superstars include Peter McLaren, Roger Bybee, Oki Lee, Larry Plank, David Crother, Rita McDonald, and Kelly Price Coley. We also have some local trailblazers from the Dallas-Fort Worth area, including Shane Woods, Linda Cook, and Malachi Eubank. In addition, we have one of our best presenters from Accelerate Learning today, Mindy Pearson. As you know, these are challenging times. Accelerate Learning and STEMscopes wants to support our hardworking teachers by offering these sessions of high-quality professional learning. Nothing in return. We are just trying to provide some meaningful professional experiences, free. We are trying to take your mind off the pandemic for a moment. Please note that the participation of our major invited speakers does not necessarily mean an endorsement of products developed by Accelerate Learning. We are in challenging times. The speakers, along with me and my colleagues, are here to provide a rich learning experience so that teachers can take back with them some information and strategies to their students. We are all in this together. Before we begin, let me share some procedural aspects to this webinar. As you know, we are using Zoom, which has a number of interactive features. Please look at the sound and video controls found at the bottom left side of your screen. Your sound should be muted. Make sure your audio has a red diagonal line through it. If you choose to display your video, be constantly aware of what you are broadcasting. We also recommend that you use the speaker view on your video display found in the top right corner. Let's try one feature now called polling. Let me release a quick poll to see who we have participating in this afternoon's webinar. You should see the poll on your screen now. If you will take about 30 seconds and mark your background. You folks are quick. Do about 5 more seconds. 3, 2, 1. Close the poll here and share the results of our participants. Primarily teachers. It looks like we've got a tie actually between pre-K 5 and 6-8 teachers. That has not happened before. We got a couple, we have one higher ed, a couple of higher ed, and a district administrator. So a nice blend of people. Thank you again for being here. Next, let's talk about chat. We will be using the chat window for your comments and questions today. The window is being monitored by our STEMscope staff, and they will be able to respond accordingly. We will also use a Zoom function called breakout rooms today. Our presenter will be able to randomly group people into smaller rooms for discussion. Okay, that's it for the procedures. Today, we are very fortunate to have Mindy Pearson present today, and an outstanding STEM educator and trainer for STEMscopes. Mindy has her master's degree in education. She's definitely a STEM advocate, coach, and professional development provider. She has 22 years of experience in STEM education. Her mission is to improve the quality of teacher and student experiences in STEM. And for Accelerate Learning, she is one of our regional STEM specialists. We are very fortunate to have Mindy share her expertise and insights with us today. So Mindy, take it away.
All right, Ken, thank you so much. I'm going to share my screen with everyone. And I want to take a moment to thank you for spending some of your precious Thursday afternoon with me. I realize that for those of us on the East Coast, it's going to bleed into the evening. And I just want to share with you that, we're here together, and I'm hoping to share some strategies that we can use with our students during this very difficult time. And so I tried to be very cognizant when I chose materials for eliciting misconceptions that we could use in the digital environment. And so without further ado, let's go ahead and get started. And so today, I hope to help everyone understand what are misconceptions. There are a lot of different types that our students might have. And I'd like to share some strategies that we could use collectively as educators to uncover those misconceptions. And then finally, how we can address those with our students once we've uncovered them. So what are misconceptions? According to the Oxford Dictionary, they just are our views or opinions or just things that we think that are just wrong because they're based on some type of faulty thinking or reasoning on our part. And so that makes us really start to think about, how does the brain work? Our brain is like this gigantic filing cabinet with files. And we try to assimilate new information by filing it into these folders that already exist. But what happens is sometimes we take in new information that doesn't fit in an established folder. And so what our brain does is it tries to refashion this new information to fit it where it thinks it should go. And this is where our misconceptions are born. We try to build explanations, we unravel problems, and we file this new data, really just based on faulty thinking and reasoning on our part. So what are misconceptions? I'd like to elicit some feedback from you. And so in the chat box, if you would, type some examples of student misconceptions that you have uncovered in your students in science. And then I'll ask Jessica to share some of those with me. Are we getting any common themes?
Well, let's see, Mindy. Evolution is just a theory. Right. Heavy things fall faster than light things. That we have summer because the Earth is closer to the sun. The Earth density is shifted because of vibration. The moon is only visible at night.
Ooh. These are some good ones. Some that we definitely will address today. So it's definitely something that we come across in our practice. And we just have to learn how to uncover those in our students and address them. So thank you for sharing some of those examples with us. So now I have a true-false question for you. And you have a participants button next to your chat box, I believe. And you should have the option to choose yes or no. And so yes, I'm going to ask you to indicate if you think that item is true, and no for false. And here's the prompt. The longer a misconception remains unchallenged, the more likely it is to become entrenched. True or false?
So we have some numbers coming in. Let's just give it a little time there. So we have 30 yes and 1 no.
All right. And so this actually is indeed a true statement, right? Research suggests that when we repeat an activity along the same lines of that misconception, we strengthen our neurons' connections. And it doesn't matter if that connection is accurate, if it's premature, or if it is erroneous. And so the takeaway for me is that misconceptions are really pervasive. All right, so I have another true-false question for you. We're going to vote in much the same way. Here's this one. Traditional instruction is an effective way to help students abandon their misconceptions. And I should kind of define traditional instruction. I went to school in middle and high school in the 80s and 90s, and I was taught traditionally, I would say. I'd go into class, I'd sit down in my seat. My teacher would probably give us some notes on the overhead projector, so I'm telling you a little bit about my age. And I would write those down, and then I might get my science book and read a section in a chapter, define some vocabulary, and answer some questions. at the end of the section. And so that's what I mean by traditional instruction. And so my question to you is traditional instruction an effective way to help our students abandon their misconceptions? True or false?
We have an overwhelming amount of false.
All right, well, that was easy, right? So let's explain this though. This is a graphic from the Journal of Science, and the references have popped up on the screen below. And while this is a study in higher education, I am going to argue that it is still very true for those of us in the K-12 arena. I served in my previous life as a science coach, and I visited campuses and many classrooms, and this trend was still, unfortunately, very true. And we're looking here at the STEM disciplines. And it's ironic to me that math is actually doing the best job right now of focusing on student-centered instruction in the higher education environment. And so in the chat box, if you have any ideas like, why is this still occurring, even though we know that it's not best practice? I'd like to know what some of you think.
Because teachers don't want to change, or it's just easy. You know, we have all these time constraints. Maybe it's just a bad habit that we have.
Absolutely.
And it's just really hard to change.
Change is hard, right? And we're in the midst of a big change. And some of us, we teach like we were taught, right? And I explained how I was taught to you. And, while that worked for me, that does not work for a lot of our kids. I know that we face enormous time constraints. It feels like, we have to teach, 14 units in 3 days. And it's hard to release control of the classroom when you have those time constraints. And so these are just some things that we have to consider as we move forward, that if we really want to develop connoisseurs of science and STEM, we really have to relinquish some of our control back over to our students. So what are the types of misconceptions? The National Research Council identifies 5 types: preconceived notions, non-scientific beliefs, conceptual misunderstandings, vernacular misconceptions, and factual misconceptions. So let's take just a few moments to kind of review what those are. So preconceived notions are just the things that we believe based upon our everyday experiences. And so an example of this would be that young children have a really hard time accepting that the earth is this sphere, because they interact with an earth that is very flat, right? And so we have those preconceived notions. We also have non-scientific beliefs, and I'm just going to put it out there. It's not necessarily our responsibility to address non-scientific beliefs in our students, but we do have to understand that our kids do come to the classroom with beliefs sometimes that are not grounded in science, but they're grounded in religion. And so an example of this is obviously the creationist timeline is very different from the evolutionary biologist timeline. And so we just have to be aware of that when we address this content in science, and we need to present the evidence for the evolutionary biologist timeline and then probably leave it there. So the next type of misunderstanding is a conceptual misunderstanding, and these arise very often in the classroom. These are the ones that I ran into the most often. And these occur when kids are taught science kind of in a superficial way. It doesn't really provoke them to confront, their understanding. It doesn't provide any cognitive dissonance. And so kids aren't really forced to really think very hard about the content. And sometimes, with our good intentions, we actually predispose our students to some of these. So an example would be the sun rises in the east and sets in the west. And while that is a true statement and you can observe that, it's not really scientifically correct, because this makes students think that the sun actually moves across the sky, which we know is not the case, right? The sun appears to move across the sky due to the Earth's rotation on its axis in a counterclockwise direction. So next we have vernacular misconceptions, and that's just because English is a wacky language. And we have a lot of words in the common life that mean something very different than they mean scientifically. And then we also have phrases. I'm going to share this one with you because my mama always told us this as kids. She had a pool in her backyard, and we were always very excited to get to the pool. And so we would run out the door and we wouldn't shut it. And she would yell at us, "Hey, shut the door, you're letting the cold out," right? I'm sure you've been told that at some point or the other. But Memo really should have said, hey, you're letting the heat in, right? Because scientifically, we know that heat flows from hot to cold by those three mechanisms: conduction, convection, and radiation. And so that vernacular misconception also sometimes leads our students to believe incorrect things. So then we have factual misconceptions, and these are just like the little factoids, Jeopardy contestant type of ideas that we have in our minds. And a lot of times we hear them at an early age, they're not challenged, and so we retain them into adulthood. And so here's one. I bet there are some people in here who believe this is true. Deoxygenated blood is blue. And how many of us have a model like this one in our classroom, right? Here's a heart model. The arteries are in red. Arteries carry oxygenated blood away from the heart, except the pulmonary arteries, of course. And then veins carry deoxygenated blood back to the heart, except the pulmonary veins, and they're colored here in blue. And while we understand what the model is doing here, it's trying to differentiate between the two types of vessels, it may help to perpetuate the misconception that deoxygenated blood is blue because they're carried by veins, and the veins are blue in this model. And then, of course, we have this example, right? If you turn your wrist over as you're sitting here at your computer and you look at it, you're looking at veins in your wrist, and they appear to be greenish or bluish in color. So deoxygenated blood must be blue, right? So then we get to this example, and this one could help actually correct the misconception. This is a person giving blood. Blood is collected by venipuncture, so a vein is punctured. It's a closed system, the needle to the tube to the bag of blood. And so this is definitely deoxygenated blood being collected, and blood, in fact, is red. It is always red. So we have these factual misconceptions. So what is our role, right? So as educators, we have to really think of ways that we're going to identify our students' misconceptions. And then we have to be very careful and plan, great learning experiences for our students that require them to confront those misconceptions they have. And then finally, we have to help them make corrections in their file folders in their brain and help them reconstruct new schema and file the knowledge appropriately. So today we're going to just look at some strategies that we can use to do that. And I've named these, you might know them elsewhere as something else, but I'm going to call them ask, then listen. We're going to look at some formative assessment probes, predict, explain, observe, explain, confronting misconceptions with evidence, agree, disagree with evidence, using models and manipulatives, which will be very important during this digital time, and then finally, multiple choice, feedback, and reflection. So let's move to this one. This one was actually mentioned earlier. What causes the seasons, right? And the very popular misconception is that we are closest to the sun in the summertime, and so it is summer, right? And so we're going to use this to model the strategy, ask the question, then listen. And so as you watch this video clip, I want to show you the source. It comes from Misconceptions YouTube channel. There is a gentleman, he's a professor, and he has put lots of great STEM videos up for kids, but then also he has a whole misconceptions playlist, which is where I've pulled a lot of the videos that we're using today. So as you watch this video clip, I want you to watch for all the players. There are a bunch of different adults. The lady shown now is who I like to affectionately call our shopper. And I want you to just kind of jot down or make a mental note of the different misconceptions these adults have. And then after that, we're going to get into some breakout rooms to discuss what misconceptions did we see and hear, and then finally, how can we start to address those? So I'm going to start the video now.
Why do we get the seasons? The seasons? Because of the atmosphere?
To be honest with you, that's a very easy question to answer now. We really don't get seasons anymore because of global warming. I think there was a time when I was a child where we definitely had 4 seasons. I think now we get summer, 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 and a little bit of winter in Australia.
Is it to do with the Earth turning and the equator? 4 seasons?
You mean like summer and winter and autumn and spring?
Doesn't that come from where we are around the sun? And at that stage, that's the season that we're in.
I think it's the position of the Earth, depending on the sun, it's like if the Earth is standing other positions to the Earth, and there's winter, summer, and in the between there's autumn and spring.
Because the Earth rotates on an axis, right? And I think, so it goes around on an axis.
Well, obviously the Earth isn't like spinning like It's like that. It's sort of like on an angle because of the axis of the Earth rotating. The Earth rotating around its axis.
Yeah, what does the axis do?
It seems to be further and closer to the sun.
For example, now the southern part, Australia is winter now, and Europe is in the summer season, and then the north side of the Earth is standing more close to the sun, and the south side is like far away from that.
It's because the Earth is at I think it's a 22-degree tilt or something like that. So as it goes around the sun, that means that either the north or the southern hemisphere is close to the sun, so that things are hotter or colder.
When the Earth goes around the sun, it's not a circle; it's an ellipse. So we have different distance to the sun.
So therefore, the further the sun is away, the colder it is in a country.
Like it's because it's like an oval. It's not like perfectly simple. It's like so the sun comes closer this way and it's out further, gets closer.
The elliptical pattern of the Earth and the distance from closer to the sun in summer and the furthest away from it in the winter.
All right, so I'm going to pause it there, and I'm going to ask Ken to deploy us into our breakout groups. And in your breakout group, just discuss the misconceptions that these adults have and how we should address them. Because ultimately, not one of these adults has the cause of the seasons correct in their thinking. And so, Ken, based on another number of participants, I would say put 7 or 8 per group. So maybe 10 groups, and that should work for us.
Okay, Mindy, I have 12 rooms and we will have 6 to 7 participants in the room. So let me deploy those, and if you all will please join your breakout room to have that discussion. Thank you.
right, and I think that we're all making our way back into the main session. I see our participant number increasing. I had the pleasure of being in breakout group 8, so thank you to my colleagues who shared your amazing ideas when we were together. And so some of the misconceptions that came up are populating on our screen now, and if we've missed any, definitely put that in the chat box and have Jessica add that to our discussion. But obviously we had the first gal who was clueless. She thought our atmosphere caused the seasons. And then we had the cool dude with the beanie cap who said that global warming is preventing our seasons altogether. There were several people who picked up on, you know, the Earth's elliptical orbit, and they believe that that was responsible for causing the seasons because it changed our distance to the sun. We had others who spelled out that Earth's distance from the sun causes the seasons. We're the closest to the sun in the summertime when it is the hottest here in the Northern Hemisphere. And we had some people pick up on Earth's axis is tilted. It's not straight up and down as the cause for the seasons. And but they attributed that to changing our distance to the sun rather than some other factors that it impacts, that affects our seasons. And so some of the things that came up in our group to address those were we would just have to have kids, you know, develop and use models and work through this process. And I'm going to ask you to populate to the chat some other ideas that were coming up. And if Jessica, you would share those with us as they populate.
Certainly. So we'll give it a little bit of time, but one thing we talked about in our chat session was, you know, the use of models and talking about the limitations of those models.
Right. Yeah, there are definitely benefits and limitations to all models. And astronomy is particularly notorious for having limits to our models, but we can't do much better because it's such an abstract concept.
Mm-hmm. And looks like we have another one. Oh, having kids model it themselves. Mm-hmm. Have students apply prior knowledge from class to discuss why each adult was incorrect. Act it out, draw it out, non-examples.
Absolutely. So we're going to have to provide kids, the point is, some learning experiences that help debunk those common misconceptions. So we're almost going to have to prove to them that the things that they believe are correct are actually incorrect. And then we're going to have to find ways to reinforce the actual correct answer. And so that first strategy really is just ask the question and listen, because when you listen to your kids and you give them the opportunity to speak, you can learn a lot about what they're actually thinking. And so I'm going to share with you some sources for assessment probes. And the first one is from the AAAS. And so I'm actually going to navigate to this site. Whoops. Let me come back here, find my mouse. And this will take you to a landing page that looks like this one. And we were going to promise to send all of these resources to you in one Google Doc. I just need to unlock it so that everyone who has the link can open it. And so when you land on this page, you are going to get the different genres of science. And what this is this is a really vetted item bank of questions that have been deployed on many different assessments. And the AAAS has collected data on a lot of student responses in different grade levels. So I'm just going to go to weather and climate, because that's what we were just talking about. And then you'll land on a screen that looks like this. And this has kind of statements of all the things that we would expect our kids to know with regards to climate science. And so, for example, I'm going to scroll down here. Here's one. The Earth's spherical shape causes differences in the intensity of sunlight and thus the amount of energy from the sunlight to be greater at some places than at others. And this really was what most of our adults were missing in that video, right? And so if you click on this, it is going to take you to a series of assessment questions along that content. And so you can click on any of these. And then on this first screen, we also can see the percentage of students in grades 6 through 8 and 9, 12 who are answering questions on this content correctly. And we can see that even in the secondary grade levels, most of our kids struggle with this content. And so I'm just going to click on one of these to show you what it looks like. So we'll get an assessment question. It says there are no clouds above place 1 and 2, and then it's going to ask them at which place is the sunlight more intense, and then they have to make their choice. And so one of the great things for us here is that it gives us the correct answer, but it also gives us the common misconception that our students are going to be tempted to choose. And then, we can look into some more data about the performance and looking at the distribution of correct and incorrect responses by grade level, by gender, by primary language. And then, of course, for those of us who are in NGSS states, I'm not, I'm in Florida, but it will also take you to the standard in the framework that is addressed with this particular item. So I've not played a lot with this, but you definitely can build your own item bank and deploy your own tests through the AAAS. And this is a free resource that is available to all of us. And so I just wanted to share that with you because I thought that that was kind of a neat resource that you may not have considered in the past. So next, I'm sure that you all have seen these, right? Paige Keeley has published a series of books. They're called Uncovering Student Ideas in Science. And then she has specialized editions like this one, Uncovering Student Ideas in Astronomy. Her co-publishers vary by edition, but these are published by NSTA Press. And when I was in the classroom, I used these quite often with my students. And one of the nice things about it is they've done their research. They know what misconceptions students have, and they also have been able to parse the typical misconceptions into tinier pieces so that we can really dig in and see where our students' thinking is going wrong. And so if you look at the example here, I know it might be small, so you might have to put your super spidey vision eyes on, but basically it's telling us the Earth's tilt's the cause for the seasons, and then it's asking us as students to determine which of these explains why the Earth's tilt causes it to be warmer in the summer than in the winter in the Northern Hemisphere. And so we have some choices here, right? So as the Earth circles the sun, the direction of the tilt relative to the plane of Earth's orbit gradually changes. That is false. The tilt is consistent. B says the direction of Earth's axis always stays the same as we circle the sun, so that's true, right? So we would hope our kids would choose that. C, when the Northern Hemisphere tilts towards the sun, we are closer to it, so it is warmer. Common misconception, right, friends? And then we have D, when the Northern Hemisphere tilts towards the sun, the days are longer, so there is more time for the Earth to warm up. That is a true statement. That might be a learning experience that we have to develop for our kids. E says when the Northern Hemisphere tilts towards the sun appears higher in the sky viewed from the United States, so sunlight is more concentrated and intense. That is also a true statement. So something we might have to design in a learning experience so kids understand that concept. And then of course, letters F, the Earth's tilt causes the sun to be directly overhead at noon in the summer when viewed from the United States. That is a false statement, as is G. As the Earth circles the sun, it changes the angle of tilt during different seasons of the year. And again, the Earth remains consistent. The Earth's tilt remains consistent. And so I would just encourage you, if you've not looked at this as a resource before, I found it a very valuable resource in my classroom. And again, that's called Uncovering Student Ideas in Science. There are at least 10 different editions, and they're not all written at the middle and upper grade levels. There are editions written for elementary and even primary grade students. And so I encourage you to consider that as a resource in your classroom. So the next strategy that I would like to look at is just predict, explain, observe, and explain. And it sounds like, it is exactly like it sounds like. You're gonna make a prediction. And so in a moment, I'm gonna show you a video, and the professor is gonna ask you, how do you think the slinky is going to fall? And I'm gonna ask you to make a prediction, and we're gonna deploy that through a poll. And I want you to explain, so rhetorically to yourself, think about your own thinking. Why do you think your prediction is true? Then we're going to observe what happens, and then we're going to make refinements to our explanations once we have listened to the scientist. And so let's deploy the video.
Today I'm at the University of Sydney talking to Rod Cross, who's done physics for many, many decades.
You are perfectly correct. I was a student here in 1960.
Wow, so he certainly knows a lot about physics. And today we're doing an experiment involving a slinky. Can you tell me about it?
Well, I have here a slinky in my hand. I'm going to hold the slinky by the top end, let the bottom end go so the slinky stretches.
And it dangles freely.
And I'm going to ask the question, what happens when I let go at the top end? Will the bottom end fall first? Will the top end fall first? Will both ends fall together? Or will the center of the slinky stay at rest and the top end and the bottom end approach each other and they collapse in the middle. Make your prediction and then I'll drop it. Ready, set, go.
All right. And so Ken or Jessica, would you deploy that poll and let's solicit some answers on what do we think is going to happen? And to yourselves, I want you to think about the reason why you think that.
Okay, I'm ready to deploy the poll on the Slinky. Here we go.
Right.
One choice. Don't be swayed by the people responding.
No. Some of us are going to be wrong for sure.
Okay, let's take about 15 more seconds. Wrap it up if you haven't voted. About 60% of you have voted.
Mm-hmm. No names are showing up here, so vote freely.
It's all anonymous.
Yeah.
5, 4, 3, 2, 1, close. And let me share the results.
Great.
There you go.
All right, so it looks like the vast majority of us, 50%, believe that the ends will fall together. And then we've got one person who thinks the bottom, or four people or 9% think that the bottom is going to fall first. 16% think that the top will, and 25% thinks that the ends will approach and it will fall as a unit. So let's find out.
Today I'm at the University of Sydney talking to...
Let me get to the next slide. Here we go. All right, so as you watch the demonstration, I want you to determine what happens and make a comparison to your prediction that you just made. Did it affirm what you thought, or does it tell you something different? And then, of course, we're going to listen for the explanation from the scientist, and then we may have to make some revisions to our explanations based upon what we see. So
Mindy, can we see it one more time?
But this is going to be really tough.
Can you see what one more time?
Go ahead. I'm sorry. Go ahead.
Okay.
To see. So how are we going to actually determine what the right answer is?
If I were to drop it now, it would happen so fast you wouldn't really see clearly what's happening. So I've brought along my slow motion camera and you'll see it at 300 frames per second, and it's quite spectacular.
Well, that's ultra slow-mo. So that's exactly what we need to sort out this problem.
We'll give a countdown because it happens really fast.
All right.
3, 2, 1, drop.
Wow, did you see that?
I didn't really see which happened first. No, I need to slow that down.
Well, let's go to a slow motion replay and see what actually happened.
So, whoa, Nellie, how many of you are just surprised by what happened? I know that when I saw it the first time, I was quite surprised. And so obviously we're all now making some corrections to our thinking. Some of us have discovered that we were incorrect. And I know now that I'm really wondering, well, what's really happening here? So let's continue.
So from the slow motion camera, we can clearly see that the bottom end stayed completely stationary even after you let go of the top. It waited until the whole slinky had collapsed down to the bottom before it itself moved downwards. How do we explain that?
Well, there are a number of explanations, but the simplest explanation is that the bottom end is sitting there minding its own business with gravity pulling it down and tension pulling it up, equal and opposite forces, no motion at the bottom end until the bottom end gets the information that the tension has changed. And it takes time for that information to propagate down through the slinky to reach the bottom end. So it's propagating down as a compressional wave.
And we saw that compression wave travel down, and it has to reach the bottom before the bottom even knows that you've let go at the top.
Correct.
And that's when it knows to start falling.
Correct.
That's a really remarkable finding. I mean, does this apply to any other objects, or is it just slinkies?
No, it applies to the real world, particularly in sports, which is the field I'm interested in.
So I'm going to pause it there, but the scientist goes into how it applies in sports, such as in baseball and golf and tennis, and how when we strike the, the tennis ball, for example, we don't even know that we've struck the ball until quite a time after it's happened, and the ball's almost all the way over the net. And that has to do with the principle that was shared in this video. And so this is another idea that we could use with our students. It especially works well with discrepant events, such as this one, and gets kids to think about making predictions and explanations, and then also kind of just sets the culture that, sometimes we're incorrect, and that's okay. We have to look and seek for evidence to explain thinking and to explain the phenomena. All right, so the next strategy that I'd like to look at is we have to confront our students with evidence. And I'm going to argue that we're going to have to do it more than once. And so this is a very popular misconception about the appearance of the temperature of objects. And so here, the guiding question is, which is warmer and which is colder? And as we watch, let's consider what's the misconception that's being addressed in this video clip. How did the presenter or our professor here uncover it? And how did he address it with his audience? And so here we go.
When you touch an object and it feels warm or cold, what is that really telling you about the object? Here I have a metal hard drive and a book. And I'm going to ask people to compare their temperatures. Which one do you think will feel warmer, the book or the hard drive?
The temperatures.
Yeah, tell me if one is hotter or colder, or if they're the same temperature. How do they feel?
This is slightly cooler than this one.
Yeah. Oh, that's warmer. Yeah.
Yeah, agreed.
I'd say the hard drive is a lot colder than the book. I don't know, because the book's got more knowledge.
Why do you think that is?
Metal's normally a little bit chillier if you leave it in a colder temperature.
Well, what if I said that they're both at the same temperature? What would you say?
So you're lying.
But really?
I think you're lying, yeah.
Oh, jeez. Well, maybe the way I could prove it is I have an infrared thermometer. What do you think we're going to see?
I think science might be able to answer that. And I'm not a scientist.
Make a prediction for me.
I still think that's cool, though.
Would you bet me money?
I don't, because I don't have any cash, so yeah.
Let's measure the temperature of the book.
Okay.
What do you see?
19.0.
Okay. And measure the temperature of that.
19.0. All right, well, now I believe you.
I'm trying to actually figure it out, trying to figure out why they would be the same temperature. They don't feel the same temperature, though.
So why does that feel colder if they're basically the same temperature?
Good one. You got the answer?
Well, I'm coming to you guys for answers.
Whoops, I apologize, guys. I didn't mean to do that. I'm having trouble with my mouse. So I want to pause it there. Let's just talk for just a second. This is definitely something that we could do with our students in the distance environment, right? We could tell them before class, find a couple of objects in your home that are metal and find some examples of objects that are non-metal, right? And I'm sitting here at my desk and I've got my filing cabinet next to me and plenty of paper resources. And so I could ask my students actually to feel those and make the same prediction that the folks in the video are making, right? And so then Derek comes around and he actually pulls out his infrared thermometer and he measures the temperature of these objects. And he basically proves to the adults in this video, hey guys, this is actually the same temperature, right? And as adults here, we know that heat flows from when it's warm to where it's cold until equilibrium is reached. And so if those two objects were to, sit outside in the same environment, they would reach the same temperature. Okay, so let me see if I can get back into the video. I'm gonna have to fast forward it this way, I think. So I'm just gonna drag it. We were about right here.
I'd say the hard drive is a lot colder than the book. I don't know, because the book's got more knowledge.
Why do you think that is?
Metal's normally a little bit chillier if you leave it in a colder temperature.
Well, what if I said that they're both at the same temperature? What would you say?
So you're lying.
But really?
I think you're lying, yeah.
Oh, jeez. Well, maybe the way I could prove it is I have an infrared thermometer. What do you think we're going to see?
I think science might be able to answer that. And I'm not a scientist.
Make a prediction for me.
I still think that's cool, though.
Would you bet me money?
I don't, because I don't have any cash, so yeah.
Let's measure the temperature of the book.
Okay.
What do you see?
19.0.
Okay. And measure the temperature of that.
19.0. All right, well, now I believe you.
I'm trying to actually figure it out, actually. Trying to figure out why they would be the same temperature. They don't feel the same temperature, though.
So why does that feel colder if they're basically the same temperature?
Good one. You have the answer?
Well, I'm coming to you guys for answers.
We're creatives, not intellectuals.
Well, create an answer for me.
I'm not a scientist. Come on, you tell me.
Well, I'll try to answer that question with another little experiment. Here is an aluminium block and
Nice and cold.
a plastic block. How do their temperatures compare?
Completely different. Completely different.
Much colder.
Yeah.
Yeah?
Yeah, this actually feels colder.
Let's take this to the next level. I'm going to put an ice cube on both plates. What are we going to see?
Well, I'm guessing it would stay solid on this one and melt on this one.
So it's going to melt on the plastic but stay solid on the aluminium.
Yes, but maybe I'm wrong.
That one will melt more quickly than on the aluminium block.
Yes. I think so. I think they're colder.
Yeah, because it's colder.
Let's
I
actually...
think they're going to go the same.
All right, so we put an ice cube on each of those blocks.
Wow.
What are you seeing?
Well, it is melting a lot quicker on the aluminium.
My God, it's melting.
This is melting quicker than that one. Even though this is aluminium, that's plastic.
So which one felt colder?
That
This
one.
one.
How does that make any sense?
I have no idea, you know.
Could aluminium be bad for the environment?
How would aluminium be bad for the environment?
Well, it's thawing out the ice a lot quicker, isn't it?
So you want the answer?
Yes.
Yes, please! It's about thermal conductivity, right? The rate at which heat is transferred from one object to another. So when you felt these blocks originally, I know this one felt a lot colder.
Yeah.
But you know from the other example we did that they must both be at the same temperature.
True.
Because they've both been outside for a while. We see that the aluminium block is melting the ice faster than the plastic block because it's conducting the heat to the ice cube faster.
Okay.
With the plastic block, it's a worse thermal conductor. So heat is being transferred less quickly to this ice block, and so it's staying ice.
Okay. I believe you.
Makes sense?
Yes, definitely.
You know, in our first example, the hard drive felt colder even though it was at the same temperature roughly as the book. And that's because the aluminium conducts heat away from your hand faster than the book conducts heat away from your hand.
Sure, that seems logical.
Which makes the hard drive feel colder and the book feel warmer.
Yes.
So when you touch something, you don't actually feel temperature. You feel the rate at which heat is conducted either towards or away from you. Think about this next time you hop out of the shower in winter. It's much nicer to stand on the bath mat than on the tile beside it. Not because the bath mat is warmer, but because it conducts heat less quickly away from you.
All right, so here we had an example of where our scientist confronted the same group of adults, and he actually had to do it twice because they showed in making predictions in that second example, they really hadn't learned anything from the first, except there was one gal who predicted that the ice cubes would melt at the same rate on the two blocks. And so maybe she was starting to change her conceptual understanding, and that she realized that initially they were in fact at the same temperature, but she was not thinking about metal being a good conductor of heat and electricity, whereas paper is not, or plastic is not. And so Derek went around again, he asked questions, he listened, he asked some follow-up questions, and then he provided some evidence. The first time his evidence was with his infrared thermometer, and then the second time he pulled out his plates of aluminium, I like how he says that, right? And the plastic, and actually created another discrepant event for students to think about. And those plates are readily available to us as science teachers. So if that is something you wanted to replicate in your class, that is definitely something that we could do, right? And so confront with evidence. And unfortunately, one learning experience probably is not going to be enough to get our students to change their thinking. All right, so this is just another quick idea that you could use in your classroom, taking any multiple choice assessment item. And I'm going to ask this time about lunar phases, because this is another example of a content area that students have misconceptions about, and that what causes them. And so we would present our students with a set of multiple choice items, and they would have to determine first which one they agree with and why, but then to take it a step further, why do they disagree with the other item choices and provide their evidence? And so let's put our teacher thinking caps on real quickly. Moon phases are caused by the Earth's shadow. And so, you know, certainly the Earth's shadow and the moon, there are definitely some things that go on between those, but those are eclipses, right? And so we might need to provide students with some learning experiences to differentiate between what we see with lunar phases versus what we see with the lunar eclipse. And then answer choice B, again, incorrect. But it does happen. The Earth rotates on its axis. It does change our perception of day and night, and it changes our perception of the position of the moon in the sky, but it is not responsible for the lunar phases. And then of course, C is the correct answer. And so we want to make sure we build some learning experiences that prove to our kids that the moon's revolution or orbit around the Earth in the calendar month is what causes the lunar phases. And then the last one, maybe a lot of our young kids think that clouds covering the moon cause it to appear differently or to have different phases. They go outside and they see one night, you know, it's completely covered up with clouds, and then the next night it's not, and what have you. And so we might have to do some time course experiments with our students, show them pictures of the moon at several different hours during the night to show that even within those several hours, the clouds move and the lunar phase remains consistent on that evening. And so just the idea behind this is just to get behind students' thinking, but then also to get them to think about why the other answers are incorrect. And it's also a mechanism to help us to plan for learning experiences to show which conceptions are correct versus incorrect. So during our distance learning phase here, that we're going to have to find some alternatives for our students to interact with content. And so PBS Learning Media has some great student resources, and so I encourage you to check that out. I am going to go directly to this resource. And this is a free online simulation. And we can launch this. And we can turn on some different features. And I can forward things by a day, okay? And so it's correct in that we're rotating counterclockwise. And I can compare kind of what my vision looks like to the lunar phase. And so if I just continue doing this, students can see what happens hour by hour, day by day. And there are some student resources that go along with this for students to record their thinking on the main page. But I'm going to be completely vulnerable to you right now. I'm good at science. I have a degree in science. I chose to teach science as my career, but I have no spatial intelligence whatsoever. And so lunar phases, even into adulthood, even into the years I was teaching, was not something that I really understood because of my lack of spatial intelligence. So I'm going to be very honest with you that this model does not really do it for me, because I can understand when, you know, I'm in this position. So let me get over to it. So I can understand the full moon and the new moon, but I have a really hard time reconciling what's happening here versus here. Now I understand scientifically that yes, only half of the moon at any given time is lit, but I have a hard time visualizing the phase that the moon is actually going to be in when I do that. So I'm just going to throw it out there. Just like in the last example, one model probably is not going to be enough for our students, and it definitely wouldn't for me. And so we constantly need to think about, you know, how does this reinforce the correct answer that the moon's revolution around the Earth is what causes the phases. And so then when are students going to need some more support? So here's another example. This is the popular moon on a stick model. And I have a video here, which is the next best thing, but I would definitely encourage my kids to kind of rummage through the junk drawer or through the garage and see if they can come up with a lamp, right? Most of us have those. We can take the shade off. If you don't have a styrofoam ball, like a ping pong ball or golf ball glued to a golf tee, works just as well. And this is the model that helped me as an adult thinker actually understand the lunar phases for the first time. And so this is a video from NSTA Press. See if I can find my mouse on the screen. I cannot. Let's just try it this way. All right.
Hi, my name is Emily Morgan, and I'm the author of Next Time You See the Moon from NSTA Kids. And I'd like to share a simple activity with you that can help you understand why the moon looks different at different times throughout the month. Why sometimes it looks like a banana, and other times it looks like half of a circle, and other times it looks like a big round ball. Well, to do this activity, you only need 4 simple things. You need a lamp with the shade removed, a white foam ball, a pencil, and a dark room. The darker the room, the better. Now in this model, the lamp is going to represent the sun, and of course the white foam ball is going to represent the moon, and your head is going to represent the Earth. So let me show you how this works. We know that the moon orbits the Earth. So in this model, I'm going to get the moon, the foam ball, to orbit the Earth, my head. Notice that no matter where the moon is in its orbit, half of it is always lit up by the sun. But when the moon is in this position, I can't see any of the lighted side of the moon from Earth, my head. From this angle, you can see what I am seeing from Earth. We call this new moon. When it's new moon, we look up at the sky and we can't see the moon. It's there, but the side that's reflecting sunlight is away from us. Now, as I slowly make the moon orbit to my left, I can begin to see a tiny sliver of that lighted side. We call that a crescent moon. As the moon keeps orbiting, we can see more and more of that lighted side. We see half of the lighted half, which is a quarter moon. In this case, a first quarter moon. As we keep orbiting, we see almost the whole lighted side. We call that a gibbous moon. Then, when we can see the entire lighted half of the moon, that's a full moon. As the moon continues in its orbit, we begin to see less and less of that lighted side. We're back to a gibbous moon, but this time the light is on the opposite side. Then another quarter moon, last quarter moon to be exact. Another crescent, and finally back to new moon. And the cycle begins again. So why does the moon appear in different shapes throughout the month? Because of its orbit. The shape or phase of the moon depends on where it is in its orbit around Earth. It takes about a month for the moon to orbit the Earth. So when you look up at the moon today, know that you'll see that same phase again about a month from now. Thank you for watching, and I hope you give this activity a try. And I hope that you have a sense of wonder next time you see the moon. For a full description.
All right, so that perfect moon on a stick model, that is what helped Mindy Pearson finally understand the lunar phases, because I could visualize it and I could see it. And so maybe that's still not enough, right, for my teacher to ascertain that I've understood. And so let's introduce another model. And this is a kind of a hybrid 2D, 3D model that students would construct. This is from our STEM Scopes curriculum, the company I work for. But essentially what kids have to do is they have to label those phases, and then they have to consider the orientation on the disc, and they have to put those phases in the correct order. And I have done this activity with a group of adults, science teachers like ourselves, and we had to really, really think before we committed to where we taped the lunar phases on this model. And so providing students with some other opportunities to construct models on their own instead of just visualizing one or doing the 3D in person, this is just another idea that we can employ with our students. All right, so this is the final piece of strategy that I want to share with you this afternoon. And this is just using our multiple choice assessments that we have, whatever source you can use, and developing some questions, but doing it in a very systematic way. And so what I've done here is for lunar phases, I've come up with just a multiple choice assessment of 13 questions. And I have set it up so that questions are aligned to some specific learning goals, as I'm circling here with my mouse, right? And so questions 1, 2, and 3 on my assessment are, I can identify a lunar phase based on its pictures, right? And then the next set of questions 4 and 5, I can use our model of the relative positions of the sun, earth, and moon to determine lunar phase. And so I'm trying to kind of parse out different aspects of understanding lunar phases in my quiz. And so you can see here that my student, Damon Ray, I made that up, right? In the first question, it says, what moon phase is this? And he was correct. And he answered that it was a full moon. And so I provided him with some feedback. Yes, that's correct. Nice job. When the moon appears completely lit from our vantage point, that is called a full moon, right? And so then we get to the second question, which is on the bottom of our screen. And that is a quarter moon. And Damon, in this case, recognized that it was a quarter moon because half of the moon was lit. but he confused the first quarter moon, which is what this is actually showing us, versus the third quarter moon. So I might provide some feedback here that says, Damon, you are correct in that this is a quarter moon. However, you've confused the third quarter moon and first quarter moon. The first quarter moon, it is going to appear, the lit portion will appear like a B as the moon is being born. That's how I remember it, right? And so that is called waxing, right? And then if it appeared as a D, the lit portion, it would be dying or waning. And so I might provide him just some constructive feedback to remind him of something that we did in class. And so ultimately, what we want our kids to do is, you know, we don't want to just give them a paper back or an assessment back, and they're grateful they got a good grade, or they're highly disappointed and they just throw the paper in the trash. We want our students to understand the value of our feedback and of self-reflection, and that we all have misconceptions and it's okay to have them, and we just need to work towards correcting them. And so in this model, what Damon would do is he would go through each of his questions. He would review my feedback. If he got something correct, he would shade it in green. And if he got it incorrect, he would shade it in red. And then ultimately at the end, you know, he's going to do kind of a self-evaluation. What did I do well on? What did I not do well on? What did I get confused? And, you know, what can I do to get some help about this? Or how could I perform better or correct my thinking? And so this is just another idea that we can employ with our students, and that we're providing them some constructive feedback, and we're giving them the opportunity to really evaluate and reflect upon their own work. So I have a few departing tips for you, and then I'll take any questions if we have any. Obviously, we have to anticipate common student misconceptions, and we have to plan multiple learning experiences that will help our students to confront them. And we learned with our examples, 1 is often not enough, even 2 sometimes is not enough. And so providing students with opportunities of this content in different contexts will definitely help us. We want to encourage our kids to test that conceptual framework constantly. We want to give them the opportunity to talk amongst themselves. We want them to experiment, the opportunity to make errors. We want them to collect evidence. We want them to have cognitive dissonance. We don't want them just to believe what we said, like the girl in the video who believed him. I believe you now that they're the same temperature, right? We want kids to know and not have to believe the teacher or believe what was said. We have to revisit our misconceptions as often as possible because they are pervasive. You know, what can we do so that when our kids 10 years from now are interviewed in the videos like these, that they are not harboring the same misconceptions that the adults in these videos did. And then finally, we have to assess often. Formative assessment is easy. Everything we've done today is an example of a formative assessment. I just caution us to consider depth and breadth of our assessments. Depth meaning we need to, you know, take the content and look at it in a multitude of ways. But breadth, we need to make sure that each of our kids' voices are heard, and that it's not just a simple assessment of the whole class where, you know, we ask the Sparkle Plenties to raise their hands, we call on them, they get it right, and we assume everyone has the conception correct. And so we need to make sure that we're giving all of our students opportunities to provide evidence for their thinking. And with that said, I'm going to turn that over to Ken, and if there are any questions that you guys have of me, I'm happy to share those with you. I know that the link that was shared with the bit.ly link, it is, I just need to unlock it. And so Jessica, if you would post that link, I will make sure I unlock it right after the session. And then you guys will be able to access any of the videos. There's also a copy of this assessment if you wanted to look at it a little bit closer, so that you can look at that outside of our session.
Yeah, Mindy, lots of great comments that everyone seems really excited, saying lots of thank yous. One question, where in STEM Scopes do you find the self-evaluation tool?
It is in STEM Coach in Action. And it is under, oh gosh, I'm such a visual learner, I almost have to look at it. It's under Using Student Data is the main heading that it is under. And one thing that I can do here too is I'm gonna just edit this slide real quick, and I'm gonna put my email address on here. And so the person who has that specific question, I can respond to you personally. Make sure I'm typing my email correct. All right. And so that is my personal email address. So if any of you have any specific questions like that one, I'm happy to answer.
Thank you, Mindy. That was excellent. You shared a lot of relevant insights into misconceptions. Clearly, it's important to uncover students' misconceptions and then address them in the classroom. As teachers, we must be proactive in this endeavor. To follow up, we will now post a link to a certificate of participation in the chat window. You can click on that link or copy the link, where you can then download the certificate for your participation in today's webinar. Again, look for the link in the chat window. We will also post a short 5-question survey about this webinar. This webinar has been recorded and will be available in 48 hours on our website. It's mini-STEMposium.com, and the recording will be available in about 48 hours. A follow-up email from me will have a link to the handout from Mindy's presentation. So just wait for the email from me, and you will have a link to the PowerPoint PDF of her presentation. Please remember that we have 6 sessions available in June and 6 sessions available in July. If you go online, you can register for these free webinars. On behalf of Accelerate Learning and STEM Scopes, we greatly appreciate you taking time to participate in these learning experiences. We thank you and be safe.